All right, welcome everybody. So far we've been discussing null and column and row spaces for a given matrix. Now we've just kind of extended our definition of linear transformations to be not just from Rn into Rm, but we're considering linear transformations from any vector space V into any vector space W. And for each of these linear transformations, we'll see that we do have a matrix representation of it. And so corresponding to these linear transformations, let's also think about how we can define this notion of a null space and a column space for a linear transformation. So let's start with the null space. So we say the null space of a linear transformation T, and we often will call the null space the kernel of the transformation as well. So the null space is the set of all vectors in the vector space V that get mapped to the zero vector in the codomain, which is W. So recall here, this map T is mapping from V into W. And so we define the null space, or the kernel of T, to be the subspace of all vectors V in the domain in the vector space V, so that when we apply transformation T to that vector, we wind up with the zero vector, and here we're referring to the zero vector in the codomain, which is the vector space W. So that's why I put a subscript W here. So we're trying to find all of the vectors in vector space V that get mapped to the zero vector in vector space W. So it's the same exact idea as the null space for matrix A. And if we want to think about the range of this map, then the range, or also called the image of this linear transformation T, is going to be the set of all vectors W in the codomain for which there exists some vector V in the domain for which V gets mapped to W. So we're trying to find all of the vectors W in our codomain for which there exists some element in V that gets mapped onto W. So we can write the range of T, which we also call the image of T, as the set of all elements TV, right? So this is what we get after we apply the map T to the vector V. So this is going to be a subspace of the codomain. So we've already considered the range of a transformation. The range is a subspace of the codomain. The null space of the map is going to be a subspace of the domain. And so as with null spaces and row spaces and column spaces, I think the best way to get comfortable with these definitions is to take a look at some examples. Okay, so let's consider the following example. I have a linear transformation T, which is mapping from the vector space R2 with the usual vector addition and scalar multiplication into the vector space of 2 by 2 matrices with the usual matrix addition and scalar multiplication. And this map is going to be defined by, we're going to take vectors A, B, and we're going to map it to a 2 by 2 matrix where the first entry in the first row is A. The second entry in the first row is A plus B. And then on the second row, we have the B followed by B minus A. So that's our map. So given values A and B, given a vector A, B, and R2, we now have a way of determining a unique matrix in the vector space of 2 by 2 matrices. So first we want to think about what would the null space of this map be? So what is null of T, or also what we call the kernel of this transformation? Well, we want to figure out what are all things A, B that get mapped to the zero vector in 2 by 2 matrix world. So the zero vector over there would be the matrix, the 2 by 2 matrix of zeros. So this is what we're calling the zero vector in W. And so in order for a point AB to get mapped to the zero matrix, we can see, first of all, A is going to have to equal 0 from this position over here. And b is also going to have to equal 0 from this position over here. And any vector in R2 that has a not equal to 0 is not going to get mapped to the 0 matrix, or any vector in R2 that has b non-zero is going to wind up getting mapped to a non-zero matrix. So we can see here the null space of this map T is just equal to the 0 vector that lives in R2. So the null space is just this one unique point, and there are no other vectors in R2 that would get mapped to the zero vector in 2x2 matrix vector space. For the range of this map, we can write this range using set notation. So the range of T is going to equal all matrices of the form A plus B, B minus A, where A and B are real numbers. So that's how we can write out the range of this transformation. And let's give one more example a shot before we move on to the next topic. Okay, so now let's take a look at a linear transformation T that's mapping on vector spaces of functions. So the domain of this map is going to be the set of all differentiable functions with the usual addition of functions in scalar multiplication. And we're going to map onto the set of all continuous functions. And this is a vector space when we equip these functions with the usual addition of functions and scalar multiplication. And so our map is going to be, let's take some differentiable function f and map it to its derivative. And if a function f is differentiable, then its derivative will be continuous. So this map is going to be well defined. So what we'd want to think about are what are all of the functions t of f, and again, this map would say, let's take the derivative of this function. What are all such functions that have derivative equal to 0? Well, for any function f of x, which is equal to a constant, right? We know that the derivative of constant functions are equal to 0. So in this case, we have that the null space of this transformation T is the set of all functions f of x equals c, where c is some real number. And any function that is not a constant function, right, it's going to have a derivative which is non-zero. So this tells us the null space of this map. Now, if we want to think about the range of this function, so this is going to be a subset of the codomain, which is the set of all continuous functions. And you might be tempted to say that the range is going to be all continuous functions. But let me throw out an example here where let's let g of x equal e to the x squared. That is a continuous function. Looks nice enough. We might want to think, okay, is there some function, some differentiable function, so that t of f is equal to e to x squared? So is there some function that when I take the derivative of it, I get e to the x squared? Well, if so, then that function f would have to equal the integral of e to the x squared dx, right? Since taking the derivative of both sides should give me e to the x squared. And this has no kind of analytical formula for this. So the point here is not every continuous function is the derivative of some other function. This is actually a really special property. So the range of this transformation T, I can therefore write as the following set. It's going to be the set of all functions g of x such that g of x is equal to the derivative of some function f of x, where f just denotes some differentiable function.